So welcome to the final webinar for July, and for the summer we'll have one in September, but not in August. We're taking a break to give everybody time to have vacation and enjoy themselves. And this is otherwise, if you guys insist on a webinar, then I'd be happy to host it. But today we have Nico. Uh, so sorry, Nico, this was the nicest picture I had of you. This was Nico and I when we went down to St. Louis to go see the eclipse. And well, here we have an astrophysicist and director of astrophysics for the summer science program, Dr. Nico Adams. He'll be presenting on searching for clumps in our cosmic backyard, the Galaxy Zoo Clump Scout project. Now, a little bit of background on Nico and myself. Nico and I are very good friends. We're also project partners. We have a antique late 19th century telescope here at the University of Minnesota, and when I was training to use it for public observing nights here at the university, Nico was the one who trained me on it. He also wrote a paper about the museum's history, and through conversation and time spent together, also throwing books at WASPs, that's how we became friends, we started to find a shared interest in the history of the museum and history of the telescope, and the possibility of designing a museum for it using some antiques, old telescopes, transits, chronographs, which we now have our hands on and are in process of doing that. So Nico, I'll give you the floor since I've given them the background, and have at it. Let me stop sharing and give you share permissions.
Thank you so much, Christina. And that was genuinely the nicest introduction that I think I've ever gotten for a talk. So I am going to do my best to follow that up with a fun talk. So this is, I will be honest, a really busy time for me. So I'll give my introduction now, which is that, like Christina said, I'm Dr. Nico Adams. My current job is as the Director of Astrophysics for the Summer Science Program, which is a program for high school rising seniors to do genuine, authentic research on near-Earth asteroids. And that is running as we speak. I'm currently in the middle of operations. So if I'm a little more scrambled, then certainly I am used to, hopefully not you are used to, but maybe more scrambled than you are used to in seeing these talks. I apologize, and I'm doing my best. And what I'm presenting today is my PhD thesis modified to fit an audience that is not judging me to determine whether or not I can graduate from my program. So it's a little bit more fun, there's a little bit more context, and I did my best to make it accessible to a group that studies Kilonova instead of galaxies. So I want to ask a few questions first. The first is just a logistics question. I have about 45 minutes and then time for questions at the end. Is that a good timeline? And second question is, has there been a talk on, or is there some general knowledge of, and you can speak up, by the way, if you have your microphone on, because this is a small group, galaxies in general, because this is a very galaxies heavy talk. Or is that going to be a new subject for these talks?
We have not had a cosmology talk yet.
Okay.
We had one on GRBs, but not, and the history of GRBs, but not on cosmology specifically.
This will be a little different than cosmology, but I think that answers the question. That's good to know. So I will make sure I'm not assuming information. And if I am and you have questions, please do raise your hand. This is a small group. It's really helpful to me. There's nothing better than seeing someone ask a question when they're confused. And there's nothing worse than finding out at the end of a 45-minute talk that I've been talking to no one who understood. So I will always say that at the beginning of talks. We're all friends here. So the talk is called Searching for Clumps in Our Cosmic Backyard. And it's based on my PhD thesis work, which finished up about a year and a half ago now, and is currently launching into a new phase. So part of the reason that this is exciting to present about is that shortly after I finished my PhD defense, we submitted a grant proposal for a project very aptly called Clump Scout 2. It got accepted. We have some seed funding for it, and it is launching, I believe, and this is unofficial news because I'm no longer part of this team, so I don't know if this is true, but I believe in this fall, and I almost certainly within this year. So this is something to look out for if this is interesting to you. There will be more work to do on this very soon that you can get involved with, regardless of your current level of expertise. So all that preamble aside, I've got this nice little image down in the left that says Zooniverse. And the reason is that this project was very, very firmly rooted in a website called Zooniverse. Hopefully you are familiar with this. If you're not, this is one of the biggest hubs for citizen science on the internet in general. And the citizen science that it does looks a little bit different than I think what this group typically does. Zooniverse is an enormous hub for all sorts of internet-powered citizen science projects that anyone, regardless of their level of expertise or equipment, can log on, take a short training, and get involved with. The numbers are immense when it comes to this. There are 903, this is screenshots I took this morning, so I believe this is true, 903 million classifications submitted of objects of all sorts. And it's not just space, although we'll focus mostly on space. That's a huge number of disciplines, from transcribing text to looking at coral reefs to doing all sorts of projects that I believe there's one that's just called Penguin Count, where you count the number of penguins in an image. There's a lot of stuff that you can do on a platform like this. Here are some of the most recently launched space-related projects, and they cover everything. So everything from the most recent project, Rubin Comet Captures, where people are literally looking at Rubin images that are coming out this month and trying to spot comets, to basically everything at every other level of size, of discipline, of study. Everything is a part of this. And where I fit into this is this tiny little corner that used to be the entire thing. It's called Galaxy Zoo, and this is the thing that started the Zooniverse. So I'll give some context for this. Back in 2007, there was a conniption in the Galaxy world because there was a very, very significant problem. We could not deal with the size of the data sets that we were dealing with. And before I go into that, I want to just give a quick overview of why we even do this. Galaxies are a very, very difficult beast to tame in science. They're very messy. They're extremely far away. I think the case for studying them is genuinely not obvious. This is actually how I started my PhD thesis defense, by the way. I just immediately took apart the field that I was in, and I was like, it's crazy that we do this. It's a really difficult thing to study. It's messy, and it's hard to get good data out of it. So I want to make it clear, why do people study galaxies? Why does this field of astrophysics exist? And why does it deserve attention and funding and all of the work that we put into it? And there's a very simple reason for it, which is that if you do a census of the matter in the universe, 84% of it is dark matter. It does not interact with light at all. If you just put that into a universe, this is what it looks like. It's not very interesting so far. So let's go up to above 90%. Let's add in the intergalactic medium, everything that's not a part of a galaxy, but that is made of matter. This is observed indirectly. We only recently figured out in the last couple of decades that it even exists for certain. This matter was known as the missing matter, or the missing baryons problem, for a long time because of how hard it is to detect. So everything that's not in galaxies adds pretty much nothing to our view of the universe. Right now, if we're looking up with a telescope, we don't really see anything. So here's where everything else comes from, is when you put in that last 8% of matter, the actual galaxies, the entire universe lights up. That is where all of the light and all of the interesting stuff comes from. It is extremely visible. It's extremely sensitive to local environments and conditions. The formation histories are really distinct and leave an imprint upon them. So despite how messy it is, and despite how far away these things are, they're our only way of studying anything interesting at a great distance, especially. So that's the case for galaxies. The problem in galaxy science that we were facing in the early 2000s is that one of the most important, and this is reductionist, this is one of many problems, but one of the most important features of galaxies that scientists are interested in is known as the morphology, which is basically just the shape of the galaxy. And that's the shape visually mostly, but it's the shape in terms of a classification scheme that was invented in the 1900s, just to notice the patterns that early astronomers were seeing in the galaxies spotted out there. So these three, you can identify these as galaxies by eye. They're very easy. If you imagine the problem of morphology as just what sort of shape does this galaxy have, it seems like it should be an easy problem. If you look at these three, you have a tightly wound spiral and a less tightly wound spiral on the right. It's not a very difficult problem in theory. It's a very difficult problem in practice, because this is an actual set of galaxies from the Sloan Digital Sky Survey. It's not easy to tell if these are tightly wound spirals, loosely wound spirals. They are extremely blurry. They're affected by things like resolution. They appear at 18 different angles. There are lots of exceptions. So you can't simply say, like, there are only certain types of galaxies that exist. There are so many exceptions to those rules, because galaxies are interacting so deeply with their environments that they can be sort of thrown off of the typical classification scheme very easily. So the point is, it's a messy problem. computers were not going to be able to do this easily, and the sizes of the data sets that we were collecting of galaxies as of the early 2000s was beginning to be above millions. So the problem was, how do we go through all those millions of galaxies and figure out, just on a base level, what is their morphology? Are they spirals? Are they ellipticals? Are they something else? So the project that ended up solving this was called Galaxy Zoo. This launched in 2007, and it is known as the first really big citizen science project of its kind in astrophysics. And this asked such a simple question. It just put a bunch of galaxies online and asked the internet to vote, is this galaxy you're looking at right now a spiral galaxy, an elliptical galaxy, or something else? The voting scheme was very simple. I'm oversimplifying to sort of add some storytelling flair, and it's worth looking up more about this if you're interested, because the story behind it is so much more interesting than we have time to get into. But that's the origin of it. There was a lot of interesting stuff that came out of this. Aside from it successfully classifying the entirety of a million galaxy data set in just a couple of months, I believe, there were a lot of discoveries that weren't expected, including one that was known as green peas. So this is the thread that genuinely resulted in this. Is there was a forum where you could discuss, post images from the project as people were looking through them, and discuss what was happening in those images and sort of notice interesting patterns. One of the sort of serendipitous discoveries that came out of this is people started a thread that was just called Give Peas a Chance. You'll notice by the number of times this has been read, 343,000 as of recently. It's a very, very significant topic, because this actually was the thread that led to the discovery of green pea galaxies, named after the thread, named after the pun, which are among the most unique, most highly star-forming galaxies in the local universe. It is an incredible topic of research today, and it's something that is still not fully explained. Basically, green peas are these extremely compact, are an extremely compact class of galaxies that give off extremely powerful emission lines because of how quickly they are forming stars and how hot those stars are. Again, I'm oversimplifying quite a bit for storytelling flair, but it's an ongoing topic of research. And it started because citizen scientists just noticed that there were green dots in a lot of the images off center from the galaxies that were actually supposed to be being studied. So this is where this project exists. It's part of the lineage of Galaxy Zoo projects, and it's informed by a lot of the stories that I just told. Can we, just using the power of the crowd and getting people involved in a project with minimal training and with a lot of eyes on galaxies, figure out something about what's known as clumpy galaxies? And that was basically my research project for the entirety of my PhD. So without further ado, I can jump into what that was. I'll start by just introducing you to some patterns among local galaxies. And I'll say that the punchline of these slides is that we don't really know where clumps fit into this yet. And I'll explain what clumps are in a little bit, but that's why I'm going into so much detail before I actually talk about what my part of this research is it's really important to understand what we know about galaxies to begin with. So the first couple of things I'll mention are that galaxies have a couple of very easy to measure properties. Two of them are color. Is it particularly red? Is it particularly blue? And magnitude. How much total light is a galaxy giving off? There's a very neat pattern among these in local galaxies. And by that, I mean galaxies within about 1 billion light years of our location. For those unfamiliar, 1 billion light years is also 1 billion light years of cosmic history, or 1 billion years of cosmic history. This is one of the hardest things to explain in a galaxy talk, because it's hard to get used to if you're not already used to it. The fact that when you are looking across that vast distance in space, you're also looking back in time. So when I say these galaxies are within 1 billion light years of us, what I mean is we're looking at the last 1 billion years of cosmic history, and this is how galaxies are behaving within that time frame. If we were to look more distantly, we would be probing further and further back into history. And so distance and time get very, very easily mixed up when you are doing galaxy work. Thank you. Yeah, I can get into megaparsecs as well, if that's a unit that's more familiar to people. So all of that said, within the local galaxy population, the color magnitude diagram is a very famous plot that basically shows that redder galaxies tend to exist in a cloud, in a sequence actually up here. where the larger the galaxy is and the brighter it is, the more likely it is to be red. And then there's this gap where there aren't a whole lot of galaxies, known as the green valley. And then there's this enormous cloud of galaxies, known as the blue cloud. And those galaxies are bluer, they tend to be dimmer, and they tend to be smaller. So it's a powerful pattern. It's been observed over and over and over again, and it just keeps getting stronger as we understand the local population better. And it needs to be explained. There are more parts of this as well, that things in this red sequence, the brighter, larger, redder galaxies also tend to be elliptical. They tend not to be spiral galaxies that have those nice spiral arms. Elliptical galaxies are basically just blobs of stars without a whole lot of structure. Whereas the stuff in the blue cloud is doing really interesting stuff. They have spiral arms, they tend to be flatter, they tend to have clearer rotation and more angular momentum as a galaxy. I've talked a little bit about morphology. I'll skip over this slide because it's not incredibly important for the current question, but the point is that all of these galaxies have these patterns imprinted upon them, and they all offer hints to how they got here. So what you can piece together, I'll talk about that in a second. Let me see. Sorry, I haven't delivered these slides in a while, so if I'm getting a little mixed up. What all of these mean together is that most modern elliptical galaxies formed from major mergers. This theory is the best explanation for why we see the patterns in the local galaxy population that we do. That when two spiral galaxies, which tend to be smaller, collide with each other and sort of relax into each other and form one giant blob that has been very disturbed and mixed up by that merger, the result is an elliptical galaxy. It's no longer able to form stars as quickly or efficiently, which leads to it being redder, because older stars, which exist for longer, tend to have a redder color than newer stars, which are burning their fuel faster and tend to be bluer. All of this tends to happen in higher density environments, which is going to be very important by the end of this talk. Mergers tend to happen, like collisions between galaxies where they turn into one giant galaxy, where there are galaxy clusters. And that is exactly where we see more galaxies in the red sequence, whereas more isolated galaxies, where there aren't a lot of mergers, tend to be in the blue cloud. So the picture that we have is basically that by about 10 billion years ago, which is what we refer to as redshift 2, most galaxies had already formed into their modern structure and are not changing as much as they did before. At redshift greater than 2, growth tends to be driven by mergers. So that's what you're seeing up here is the simulation that you're viewing of galaxies coming together is basically our picture of how modern galaxies formed. It started early on in the galaxy's first couple billion years with a lot of very small galaxies just assembling together and merging into one larger beast. I'll play that one more time because there's a lot going on there. At about redshift 2, there's a transition where there are still some merger events happening. There's still some agglomeration of mass, but mostly mass accretion that galaxies are building up their mass with is happening more gradually. It's not happening in these huge bites from other galaxies or these huge collisions. Mostly we have big galaxies that are either eating small galaxies, and it doesn't affect them as much because the size difference is very large, or they're just sort of gradually pulling in gas from the medium around them. And that leads us to today. The Milky Way, as we know it, is this very stable spiral galaxy. It's fairly flat, and that's how a lot of galaxies exist in the modern universe. It fits within this picture of galaxy assembly very, very neatly, where most of the mergers that are going to happen in the universe have basically already taken place. And galaxies are relaxing into their modern structure and are not going to be disturbed as often. All right, this is a very long introduction to my research, but that is the picture of galaxies that we have today. And it's based on those patterns in the local environment that we observed in very large part. So what are clumps? And what was I studying in terms of clumpy galaxies? In about the 1990s, when the Hubble Space Telescope launched, we finally got to break out of our limited picture of the universe that just looked almost entirely at local galaxies. we weren't really able before then to observe galaxies that were more than a few billion light years away at scale. So what this meant is that this is on the right, the Hubble Deep Field image is a very, very famous image. It's the one that you may know as Hubble turned to a blank patch of sky for the first time. It just took one long exposure, and the number of galaxies in that exposure was immense and larger than a lot of people anticipated. Those galaxies, and this is where my research starts, also looked different than they do in the local universe. If you zoom in on any of the Hubble deep fields, there have been a lot of follow-ups to those. They don't look like the neat spirals or neat ellipticals that we see today. They tend to look clumpy, and that is genuinely where the name clumpy galaxies came from. It's a very friendly term. It's like black hole, brown dwarf. It's a very nice word. It doesn't take a whole lot of extra explanation, as many astronomy terms tend not to. Clumps, as we observe them, were these things that we saw in very distant galaxies that were very, very large and very luminous. And there were regions of high star formation that were way beyond what local pockets of star formation were doing among local galaxies. So in the Milky Way, we might have like a pocket of star formation. If you're familiar with the Pillars of Creation image from Hubble, that's what a small pocket of star formation looks like. It's a big area of a lot of gas collecting into one place, collapsing into stars, and then those stars sort of violently clearing out the gas that formed them. And it's this complicated feedback process. It's hard in modern galaxies, which are very stable, to get that much gas compressed into one place. And what we're finding is clumpy galaxies have these regions that are 10, 100 times larger than we would expect those regions to be. And we didn't really have an explanation for that. So there was this long time where for about a decade and a half, there wasn't a consistent way of even defining or identifying clumps within galaxies. A lot of things were tried. I'll sort of skim over what some of these methods were, but people looked at them and basically just pointed out, oh, these look like clumps. That was what the field of clumpy galaxies was for about 10 years. As things got more quantitative, and as we identified more and more examples and needed a way of classifying, there started to be more mathematical ways of doing this. One of them is you can just take a science image, smooth it, and then subtract the smooth version so that only the really sharp changes in the light profile of a galaxy stand out. This is known as contrast imaging. It's a really common way of identifying clumps today. The problem is none of these actually define what a clump is, and that's also very difficult because they're distant, they're hard to study in detail, and it's hard to find a definition that fits every situation in which we might be interested in explaining why distant galaxies with these clumps are different from clumps are different from galaxies locally. So the qualities of a clump that we're looking for are, we know that they are luminous, and they're especially luminous in blue and ultraviolet wavelengths, in very high energy wavelengths of light. We know that clumps are compact, that they're around a kiloparsec or less in size. I'm skipping past kiloparsec, but please feel free to ask if you need a definition on how large that is. In morphology, they tend to dominate the structure of the host, so they are by far the brightest and most noticeable things. And in redshift, they're significantly more common far away. So whatever we define clump as, it needs to meet all of those criteria. And what we ended up settling on as a field was we just draw a circle around a clump, calculate how bright it is, and if in the ultraviolet it is a certain fraction of its host galaxy's brightness, that counts as a clump. And if it's not, if it falls below that within that circle, it does not count as a clump. It works pretty well. It's a really simple thing to calculate. It excludes most star-forming regions locally, which is what we expected. We were very surprised when we saw these in distant galaxies. Thank you, Christina. And it's also very easy to measure. So it's not perfect, but that tends to be the working definition people use today. The prevalence over time of clumps using that definition is the subject of a huge amount of debate. It looks like, and again, this is a complicated graph I won't go totally into detail on, that clumps seem to be getting less common as redshift goes down. So I haven't put timescales on this graph. I've just put redshift, which is the weird distance metric that all astronomers use. But I'll translate this. Redshift 1 refers to about 5 billion years ago. Redshift 2 is about 10 billion years ago. By the time we get to redshift 0.5, 0.2, we're looking at the last couple of billion years. So this is where sort of the modern universe exists. There hadn't really been any studies here because we hadn't found a lot of clumpy galaxies there. So all the data points we had on how common are clumps over time in galaxies were from the earlier universe. And we noticed some patterns, but they weren't very certain. We noticed that, for example, clumps tended to be more common in smaller galaxies, that they tended to be less common in larger galaxies. And smaller galaxies also kept their clumps for more of cosmic history. But it wasn't clear if these trends were real, if they would continue. It was very hard to study clumps at that distance, because looking across the universe, our data is just not as good. So one of the big questions we were trying to answer was, how are galaxies actually getting these clumps? And this has impacts. As to the picture of galaxy formation that I presented earlier, we thought for a long time, and think now, that galaxies are forming at first by hierarchical assembly, by basically mergers of galaxies forming larger objects, and then sort of settling down into sort of steadily pulling in mass from their surroundings. Where in that picture clumps fit is unclear, but it has some significant implications for that. Clumps may form because galaxies just have a lot of gas early in the universe. And so it is very easy for them to pull in that gas into a very compact object, for that object to sort of explode into this immense burst of star formation that we don't see anymore. And now, because galaxies aren't pulling in as much gas from their surroundings, they're just not as able to do that. And that's why clumps aren't as common today. It's also possible that clumps are satellite galaxies that already existed. They've formed independently from the galaxy that they're hosted in, and then they just sort of get pulled in and circle the galaxy for hundreds of millions of years, like a piece of dust circling a drain or something like that. These are both really good examples of that from the simulations we saw earlier, where galaxy on top is pulling in gas from its surroundings, and there are these little eruptions of blue light where a lot of stars are forming because all of that gas gets compacted into one place and forming a lot of new stars at once. The bottom simulation shows a galaxy that's sort of circling the drain, and they look surprisingly similar. If you pause this and you don't really think that hard about it, when you see it in motion, they look very different. And that is the point, is we don't get to see the motion of galaxies over time because this takes hundreds of millions of years. We only get to see the paused version. So telling the difference between these two formation methods was one of the major goals of this research. I'll skip through a couple of slides just to say that what we're looking for when we look for clumps is something halfway across the universe almost all of the time. And that really limits how much detail we can see about what clumps actually are. So we can't tell any structure, any detail, anything smaller than about 3,000 light years of space, because we are looking 5 billion light years away. So things are blurry. It's just hard to resolve things across that immense distance. The tools that we have, most notably the Hubble Space Telescope, now the James Webb, it can really only resolve down to that resolution, and that's still true. Unless we build a much, much larger telescope, that will continue to be true for the wavelengths that we're looking at. On the other hand, most telescopes that sort of focus on the local universe have wider fields of view, but they are much lower resolution. So they have about 10, images tend to be about 10 times blurrier. The telescopes tend not to be as high quality, or at least as high resolution. What tends to happen instead is these telescopes resolve much more of the sky. They're looking over wider fields of view. And this is a long-winded way of saying, if you look at the Hubble Deep Field, you tend to see galaxies that look like this. They're blobs, and they have a certain blurriness about them that is very similar to most ground-based telescopes and most sort of local universe-focused telescopes looking at galaxies that are much closer by, because those telescopes are covering wider fields of the sky. They're seeing more galaxies at lower resolution, and those galaxies are much closer to us. So in either case, you're kind of looking at the same spatial resolution of about 3,000 light years. We have an opportunity with the Hubble Space Telescope to delve a lot deeper than that in resolution. If Hubble just picks a couple of galaxies nearby and focuses very, very sharply on just them, it can resolve a much finer resolution than most telescopes that look at nearby galaxies. So that's the goal, is can we identify some local galaxies that look clumpy, similar to the ones that we see at high redshift, take the Hubble Space Telescope and point it at those galaxies. And how can we identify the best candidates for that? It's a very big project. The Hubble Space Telescope is an incredibly competitive telescope to get time on. We needed a way to figure out what that sample was going to be. So these are some of the big research goals that we had in mind when we launched the Clump Scout project. Is what is the big picture population of galaxies that have clumps in the local universe? It just hadn't been studied. At the same time, can we find some really promising candidates to focus very high resolution images on? So keeping those in mind, Galaxy Zoo Clump Scout basically took 245,000 galaxies that had been looked at before that seemed like they would be promising candidates for this. We filtered that down using past votes from Galaxy Zoo projects. So those are people going online and basically saying, hey, it looks like something interesting is going on within this galaxy, or it looks like this galaxy is pretty much a blob, that it doesn't have any interesting features. We used that featured vote and a couple of other criteria to filter a sample down to about 60,000 galaxies. And then we uploaded those galaxies onto the internet, and we just had people look at them and click on where they saw clumps. So this is what the classification interface looked like. We had, for 60,000 galaxies, a marker that said, this is a normal clump, and then a different marker that said this clump is unusual or interesting. It turns out most things that people marked as unusual were either noise or were stars that were in the foreground. They weren't really part of the galaxy. So this ended up being a really useful tool for removing noise and things that we weren't interested in. So as a classifier, you're asked to click first on the central bulge of the galaxy, and then on either normal clumps or unusual clumps based on a couple of example images that we provided in a tutorial. So here, for example, is our first example image that every person who took part in this project saw. It's just a picture of a galaxy, a couple of blobs of light that are mostly pretty faint are circled. And based on those tutorial images, they start classifying. We also had, hidden in this classification system, a feedback system where secretly we would intersperse in pre-classified images to the first 20 or so images that people were looking at. And we'd give feedback. We'd say, like, okay, you marked this thing. This is not something that we think is a clump. It's too far away from the galaxy. This is something that you marked, and it is something we think is a clump. And some of them we even marked as particularly faint to sort of give people feedback on, like, is this something we expect you to see, or is this something that's you really have to have an eagle eye to point out? So this is the design of the project that we put together. So those 60,000 galaxies were each looked at by 20 unique people each. And in the end, about 20,000 people were part of this project over the course of about a year and a half, from 2019 to 2021. 3.5 million locations were marked, which means that those are just the number of clicks that people left. And each image would get turned into something that looked like this. There were all these bounding boxes around where people's clicks went. It was our job after that to figure out, well, how do we turn those clicks into locations with any degree of confidence? It's a very difficult problem. It's not really solved, as it turns out, particularly not for citizen science projects like this. So we actually tried something new, known as a facility location algorithm. And I'll skip over most of what this is, but basically, in a facility location algorithm, you are establishing facilities that serve cities. So each city needs, for example, a power plant. Let's say that's the facility. You want to open a certain number of power plants and connect them to the cities that need them. And you want to do so in a way that's the lowest cost possible. So you don't want to have to lay connections that are super long. You don't want to have to open a huge number of new facilities, but you want to open enough that you've satisfied enough of the cities. It's a surprisingly good metaphor for trying to figure out where clumps were located and then connecting them to these clicks. And in the process, adding this sort of layer of complexity and intricacy led to us being able to account not just for where are there clusters of clicks, but also what patterns existed within each volunteer's clicking habits. So does this person tend to click all over the place and not agree with anyone? Do their clicks tend to be very frugal, and do they tend to miss things, or do they tend to be very accurate just across the board? we also accounted for each image's difficulty. So if an image was very, very hard to find agreement upon, and every volunteer clicked all over the place and nobody really knew what was going on, we would treat that image very differently than when where everybody sort of agreed on it. And by collecting this very complicated statistical model, we ended up with a pretty confident set of locations. So that's not what the next slide is, but this is what it usually looked like by the end. Is you'd take a galaxy that looked like this, you'd have this very messy data set imposed on top of it, you'd identify a couple of clusters that were the most promising and discard the clusters that were the least promising, and you'd end up with a final set of clumps that were interspersed throughout the galaxy. And that's where the citizen science data went, if you took part in this project, is it went into this data set, we processed it with that incredibly complicated model, and we ended up with real scientific data. So we released the entire data set at the end of that project, and it's available now, based solely upon what citizen scientists put into it. So to test this, and to make sure that people were identifying things that we were looking for, we also put in about 30,000 galaxies that they were real galaxies, but we put in simulated clumps to figure out, well, if we know how bright a clump is, if we know what color it is, if we know how bright its background is, how far away it is from a galaxy, what patterns exist in where people are finding them? And are they missing like all of the ones that are, for example, particularly faint, or all of the ones that are very blue, or what sorts of things are people catching versus not catching? We developed this relatively complicated model to figure out what sorts of objects are people catching and exactly how much are they catching them, so that we could boost the detection statistics and say, well, we think that about half of galaxies were clumpy based on what people said. We also know that they tend to miss clumps that look like this in galaxies that look like this at exactly this rate of the time. So we can boost the clumpy fraction by a certain amount based just on what we know about what volunteers did and did not catch from these simulated clumps. And all of that is to say, here's a sample of the final data set. These are all galaxies in the local universe that were, to our knowledge before this, not supposed to exist. These are clumpy galaxies that exist within the last billion years of cosmic time that are very close analogs to galaxies that existed 5+ billion years ago that had those very bright star-forming clumps. These are part of, some of these are part of the sample that is now being looked at by the Hubble Space Telescope. So we have a proposal in that's been collecting images of the most promising subjects so that we can finally get not just these blurry sort of blob-like images of clumps, but higher resolution images that show substructure of the clumps, that reveal a lot more of the behavior around the clumps. So that's an ongoing project, and we have not released any data on it or any studies on it, but it is one of the more exciting things that came out of this. So here are some of the key results. And I'll sort of speed through these because I know we're running low on time. One of them is that we wanted to know what happened in this mystery region. This is the last few billion years of cosmic time. We don't really know how clumpy galaxies are in that region, and now we have a much better idea. So what we found from the Clump Scout project is that every type of galaxy, no matter how we divided them up, had very, very few clumps. They're very rare. And it's not interesting that that's true for the entire galaxy population, but it's interesting that it's true for every type of galaxy, including the very, very low mass galaxies that until we did this work, we thought might continue to have clumps for a lot longer. So when we overlay a couple of different patterns that galaxies are experiencing on top of this, the gray lines are predicting about how often are galaxies merging together, how often are larger galaxies sort of swallowing smaller galaxies. The orange lines are tracking about how much gas from the interstellar or intergalactic medium are galaxies drawing in as cosmic time goes on. We don't know how clumpy galaxies remain over that time, but we need some trend to explain if galaxies are becoming way less clumpy here, and it's happening to every type of galaxy, which of these mechanisms best explains that? And we found that if galaxies are drawing in satellite galaxies, and those become clumps, so they form XC2, it doesn't really explain why clump formation shuts off, because we think that the minor merger rate kind of continues to be elevated for a lot longer than other mechanisms of clump formation. We do, on the other hand, have a pretty good explanation for why clumpiness shuts off if we think that clumps come from internal gas that is being swallowed at a more gradual rate. So that mechanism explains better why we see clumpiness shut off everywhere. And to add to that, we found some environmental trends that were really, really helpful. Basically, if clumps form within galaxies, we'd expect them to form in more isolated environments. If they form from outside of galaxies and then merge later, we'd expect them to have limited correlation between star formation and clumpiness. And it, I am rushing through this, and I apologize, but what ended up happening is we looked at every correlation that we could between the star formation rate of a galaxy and the rate of clumpiness of that galaxy. And
Nico,
yeah,
take your time. We usually go over a little bit anyways. It's okay.
oh, good. Okay. Thank you for letting me know. So, this is the key graph. So I do want to spend some more time here. What you're looking at on this graph, which is a monster, is the x-axis tracks the crowdedness of a galaxy, where stuff on the left are isolated galaxies without a lot of neighbors, and stuff on the right are cluster galaxies that are surrounded by neighbors. We basically expect that if something in the environment is triggering or shutting off clump formation, we'd expect to see a pretty strong pattern here, where things on the y-axis, which tracks how many galaxies are clumpy. So basically, does this galaxy have a clump of a certain brightness or not? We'd expect to see a pattern in that if clump formation is environmentally triggered. And we do see a pattern where more isolated galaxies tend to have more clumps until we start binning and separating out by other categories. As soon as you separate out by, well, how fast is that galaxy already forming stars? And what else is it doing? Then we start to see that pattern vanish, where no matter where a galaxy is, as long as it's already forming stars, which is this blue line measured in 3 different ways, it doesn't seem to make as big a difference where it is. It seems to have clumps no matter what. Whereas galaxies that are not forming stars tend to not form clumps, no matter where they are. So it was a confusing, this was, I will say, the most confusing results of my PhD to interpret. So I'll skip to the end, which is that what we see is the clumpy fraction has fallen by about an order of magnitude, so about a factor of 10, over the last 5 to 10 billion years. It happened for galaxies of all masses, and it happened for galaxies of all environments. What it didn't happen for is galaxies that are very highly star forming. So what we see is if galaxies are already forming stars at a really high rate, clumps seem to just sort of follow from that, which was a really interesting result. So we have this loose conclusion based on these patterns that if clumps are forming within a galaxy from gas agglomeration, it best explains why the patterns in clumpy galaxies are the way we see them. So I'll quickly give a look at what's next. I should stop here and ask, are there questions on what I've said, points of confusion? Have I completely lost people with parts of this talk, or is there anything people would like to ask about?
Does anybody have any questions for Nico at this moment? I have a few comments and questions, but we can wait till the end if there's like another slide you want to get into.
Sure. So this is the what's next page. So this is what's exciting, I think, in the future. The first what's next is the Hubble Space Telescope is collecting the higher resolution images of clumpy galaxies. And this is a preview of what that will probably look like. Higher resolution images of clumps tend not to look like these blobs that we've seen before. So instead of just like a spiral galaxy with stuff in it, all of a sudden you start to see that clumps are not circles, they are really highly substructured objects. So this is the best example of that one image, and we now have about 40 of these, of a clumpy galaxy where a clump is circled at low resolution. So we can only make things out to about 1 to 3,000 light years, about a kiloparsec or so. the clump that looks like a blob at that resolution, as soon as we zoom in to something more like 100 kiloparsecs, starts to be this really interesting object with lots of different parts. You can actually see how some of those parts are interacting just by eye, and there's a lot more to study there. So we now have a sample of those objects, and we are, as a group, working on a paper on that. That is entirely due to the contributions of citizen scientists who allowed us to identify the most promising candidates for Hubble Space Telescope follow-up. So all of those clumps are basically things that citizen scientists found. We are also looking at not just visual data on these clumps, but spectra, which means that we were looking at what sorts of emission lines, what pattern of light are they emitting. That will be really interesting because if you look at how the pattern of light changes over the course of a galaxy, over the spatial extent of a galaxy, you can see a lot more about how the galaxy is moving, because things that are moving away from us tend to shift their light into a redder part of the spectrum. Things that are moving towards us tend to shift their light into a bluer part of the spectrum. And you can, from that, estimate a lot more accurately what are the kinematics, the patterns of motion within the galaxy. So we are looking at those in conjunction with the high resolution data, try to figure out, well, what is happening in these local galaxies to cause such an enormous explosion of star formation in this one very specific spot. And the last and most exciting thing is that, and this is the one that I can't reveal a whole lot of information on, because it is an ongoing project that is going to launch, we hope, later this year. But this is the Clump Scout 2 project. So the original proposal for this, and the final will look a little different, is that we have a large data set of slightly higher resolution data from a telescope known as the Hypersuprime Cam, which is basically to say that we can't quite make out the level of substructure that we want to in these images, but we have so many clumpy galaxies to examine, and we have so many boosted resolution, so slightly sharper images to look at, that we want to train a machine to circle the not just spot that a clump occurs, but a spatial region that has some complexity to it. So what are the sort of interacting parts, the spatial extents of and the shapes of clumps? And machines will struggle with that at first. So we're asking people to go in and take the machine results and correct them. So we're going to sort of look at this large sample of galaxies and say, how is the machine doing? Are there clumps that it missed? Are there clumps that it misidentified? Do you need to merge two clumps into one? There's a lot more nuance to be had there, and that is a project to look out for in the future. This is something that you can get involved with, and I very much encourage you to get involved with, because I think this project will be a lot more welcoming to more in-depth engagement. What we're looking at is no longer just where are clumps, but what shapes are they? Can we classify different types of them? There will be a lot more interesting things to look at. So if you're interested in sort of spotting patterns and being the first on the scene to figure out what's happening in these very odd galaxies, this is the place to be. And that is it for me.
Thank you, Nico. What an awesome presentation. So, does anybody have any questions? I do, if anybody doesn't have any they'd like to start with. Okay, so first, conniption has always been a favorite word of mine, but it's now my favorite noun regarding specific science issues. Okay, science is having a conniption today. I like this. And then at the beginning, you mentioned that at the start of your thesis presentation, you went in and set and, kind of deconstructed issues within your specific field. And this issue that you were regarding was with the issue with galaxy science is the disparity between baryonic and dark matter. Or was there another more specific issue that you were referring to?
Oh, the conniption was way back at the beginning.
Yes.
There was a crisis due to too much data. That was what that was referring to.
Okay.
So the problem was that Galaxy Zoo originally launched. Where's the best slide to look at here? Galaxy Zoo originally launched because there were about 1 million galaxies in our image database, and until that point, because we didn't have digital space surveys until the early 2000s that were publicly available like this, we did not have to deal with that many galaxies. So the conniption was, how do we figure out how all of these millions of galaxies are spirals or ellipticals or something else consistently across the whole data set. And it was such an immense problem that it led to citizen science becoming one of the major branches of galaxy astrophysics. The story behind this is that there was a grad student who was asked to classify about a 20th of the data set. It took him a full week of working really, really long days. And in I think a British pub somewhere, he and his advisor came up with the idea for Galaxy Zoo because they were so exhausted of doing this by hand as scientists. So that's how citizen science came into the picture.
That's awesome. I know currently I've been doing interviews of our members regarding their experience and their lives, being so involved in astronomy. And a few of them have brought up the same issues that they're concerned about with the advancements in machine learning and technology, hardware and software, that citizen science will become increasingly more difficult. And my response is that it'll become more difficult for the opposite issue, not because of, it'll become obsolete, but because there's going to be so much more data that the citizen scientists are going to ever increasingly become more involved, and especially with the release of data from the LSST. And then even as technology, like the hardware involves, not just data science, but as the hardware, the cameras, the technology, more surveys, more telescopes go up into space, there's going to be the need for more manpower to really analyze these, and then in different ways, just like we see with Clumpy Part 2. Uh, Whereas we've evaluated what these are, but now we need to really study how they differ in size and shape and stuff like that, even with machine learning.
Yeah, I think there are two parts of that that sounds very familiar to what I was learning about when I was at the forefront of this field. And it's been about a year for me. So I think this has become more true in the year since I was actively doing this research as part of the team. One of them is that there is a sort of stepladder of ways to get engaged as a citizen scientist. And that is very different from the on off, either you're a scientist who has like qualifications and the academic uh, past necessary and sort of political pull necessary to get research done, versus you are a citizen. You are not involved in science at all. That was a binary that was true for most of the history of science, with contributions from amateurs being not as encouraged as they were in projects like this. So the stepladder is you can start at the bottom of the stepladder as I know nothing about galaxies. I just want to log on, look at some pretty pictures, and follow some instructions. And that's how a lot of Galaxy Zoo volunteers, the vast majority of them, by number, get involved. There are also ways to get involved more deeply, which includes you get to learn a little bit more about the subject matter, identify odd things that don't fit in the data set, help manage forums, help corral people power, and basically like take part in the science despite not quite knowing as much as the scientists who are leading it, but you get to collaborate with them at some level. And then I think there is what my understanding is that Kilonova catchers is doing, which is a lot more involved. You have to know the equipment that you're using. You have to be ready to respond to unexpected stimuli. So you are providing a source of expertise that is distinct from, but extremely vital to the science itself. You might end up on a paper itself.
We've had three
Oh,
the last 18 months.
that makes me very happy and surprises me very little from what I learned about the field. So I'm not as familiar with Kilonova catchers, but in terms of citizen science, that stepladder is something that people are keeping very much in mind. I think what's going to happen is that now that data sets are so large that at the beginning, you could publish an entire galaxy data set and just have people look at every single galaxy in it 40 times each. And that was what the original Galaxy Zoo did, because it was only about 1 million objects. So that only took a couple of months with many, many thousands of people contributing. It's not going to be possible to do that anymore with, for example, data from the Rubin, which is going to look at so much data that it's going to generate basically one Sloan Digital Sky survey, which took a few months to classify every single night, just in terms of the quantity of data generated. No human crowd, no matter how large, is going to be able to look at every part of every image. So it's going to require more expertise to have people zoom in on the parts of that that are most important. Like the discovery of green peas required people to be familiar enough with these images that when green objects started showing up, they stuck out enough that people drew attention to them, and the community was well organized enough to sort of start collecting them and forward that to scientists. And it's going to be more and more important to find people who are skilled enough to make those serendipitous discoveries and recognize them for what they are, because scientists are not going to be able to handle the flood of data. It's going to require human eyes. And I should add, machines are not going to be able to handle that either, because machines won't know to look for things that it's not already expecting. That's an oversimplification. There are some techniques for that, but human beings being in the loop is by far the best known method for identifying interesting stuff in those immense data sets. So that's my long ramble about where citizen science, I think, is going.
Awesome. And then at the end, you had the galaxies, and that were compared from the SDSS survey to the Hubble Space Telescope, to the, I forgot what the tertiary observatory was, that was cataloging these galaxies, or at least observing these galaxies. I think this was a really, really good, yes. I think this was a really, really good diagram to show the evolution and the range of capabilities of our different facilities in the world. So the SDSS, the Hubble Space Telescope, Euclid, and it just goes to show that how even despite its age, how relevant and how amazing Hubble Space Telescope really is, and then how we can see that work in conjunction with the JWST and Nancy Grace Roman when it launches, and now the LSST starting in the fall. And so we already see these working together at different scales. Then now we're going to have all these really, really powerful facilities up there, and how this is going to revolutionize our future for cosmology and for the transient sky as well.
Yeah, I think one of the most exciting frontiers of astronomy, honestly, is just the size of the data set that modern telescopes are able to produce. The trade-off on this slide between the Hubble Space Telescope and the Sloan Digital Sky Survey is that Hubble is very, very shallow. Is very, very deep, but very, very narrow. That's the metaphor. I always get those mixed up for some reason when I start to say this. The Sloan Digital Sky Survey was very wide, but very shallow, which meant that Sloan was not picking up a whole lot of light from the parts of sky it was looking at. It was not getting a whole lot of resolution. Hubble is getting a huge amount of resolution, really good at picking up light. The James Webb is many times better at picking up light. It's better at resolving light. It can look at different types of light. But both of them are very limited in the size of the sky that it can look at. I think the most interesting frontier in astronomy is just as we develop telescopes that are not as limited and can look at huge swaths of the sky at the depth of something and the resolution of something like the Hubble or the James Webb. Rubin is one category of that. It's looking mostly at, on this end, the resolution of Rubin is not that much higher than something like the Sloan Digital Sky Survey, unless I'm very wrong about that. So you can correct me, because I'm not the expert on Rubin, and that's more Christina's role. But it's of the same category, but it is just collecting so much light and looking so often that we are now adding sort of time to that as well. Like, can we look at how things change on very, very wide scales? Roger, do you have a question?
Yeah, yes, I do. First of all, thank you, Nico. This is a very interesting topic, and I'm ashamed to admit that I have not heard a whole lot about these clumps, even though I read a lot here and there. So it's highly interesting. So thank you for that. I'm just surprised that I have not heard once the word AI in this whole conversation, because it seems to me that when you deal with large volumes like this, AI always comes to the rescue. So why have you not mentioned that?
So I will be honest. Part of the reason I didn't mention it is just because I skipped over the slide where I mentioned it. So it did see some very heavy use in my PhD work. Uh,
Okay.
the other reason is that I want to emphasize the role that humans have, and that role is not going to go away. This work in particular did not use AI as in the forefront as future works will. So the other place you saw AI in this talk, I will say quickly, is Galaxies of Clump Scout 2 is going to be not a human-driven project and not an AI project, but human in the loop, where basically we're having a machine promote images to human attention. Humans are correcting that machine's classifications, and the machine improves actively, and then presents more classifications for human beings to look at. There is no future that's machine-driven only, because that feature is not going to be interesting to human beings. The problem is that no matter how good a machine we design, it's going to require human beings to input things, because if we design that machine to be extremely good at a task, the quality of the machine is only as good as the quality of the task we have chosen for it. That's a really abstract way of saying, if we design a machine to be very, very good at classifying galaxies into spirals and ellipticals, and then we point it at the high redshift universe, it's not going to see clumps. It's going to see spirals and ellipticals, and it's just going to be sort of worse at it because the high redshift universe looks different than the low redshift universe. So I think it's important to be human focused when it comes to this stuff. I think there is a lot of excitement about AI. I don't feel like I need to contribute more to that. I think we're already most of us are already there, but that was the motivation behind that. I will say that the other place that this came up in this work was that we actually did train a machine learning model. And it ended up being that the final sample of clumps that we did the final results on needed to be expanded beyond the number count that we saw early on. We just needed more clumpy galaxies and more galaxies total in order to generate high enough signal in the noise that we were looking to figure out the environmental trends that we wanted to see. So we trained a clump detector, like an object detection network, on citizen science results. And it basically was equivalent to the performance of, or similar to the performance of volunteers. It detected some things that were fainter, but the biggest advantage is that it basically increased our sample size by 5. So that was the role of AI in this project. And then Christina, I think you have your hand raised.
Yes. Another important factor, Roger, is that when scientists like myself and Nico refer to like, oh, we're using machines or we're going to be training machines, we do mean artificial intelligence, AI.
Yes.
There is a sort of Hollywood-esque attribute to the phrase AI that is not accurate. Machine learning is the more accurate term. And the reason why there's this disparity is that AI usually means like, hey, oh, somebody's like, oh, there's this personality, there's this like soul that humans have created in a machine, and that's not really it. Whereas machine learning is a very specific, highly developed algorithm. And what Nico means that the machine will only be as good as the scientists who provide the task means that machines require data, and everybody knows this. And these machine learning algorithms require data, but they require us to initially separate the training data and the test data, identify and label. So not only with this training data and the test data, it's separated into two parts. Right, both the training and the test data will have a set of parameters and then labels. And so those parameters could be anything, the distance, the shape, the size, the brightness, and then we label them. And so a combination of those parameters will have a label like clumpy or bright and clumpy, or like a type, be able to label it as a supernova or a type of supernova. And so that's why we specifically use machine learning algorithms, not the term AI, as well as there is machines will never overtake, and why machines will never overtake the human involvement aspect of this. As the science, as the technology improves, as our knowledge improves, the machines will get better because humans, it is a collective human mind there. It is not a mind of its own.
Okay, that's clear. I was just also making a parallel with what I live every day, because I do a lot of astrophotography, and we use some software, among others, called Pix Insight, and there are modules which are AI based, like from Russell Cronin or RC Astro, called Blur Exterminator and Noise Exterminator, and these are all they've all been trained on thousands and thousands of images of what noise should look like in these images and what clumps should look like, and that I use that extensively. And so it makes a very blurry picture into, the smaller, fainter galaxies in the background. Suddenly they came into life. And, so I was looking at your images and it reminded me, geez, I could use this image, feed that into my software and make it something that would identify the clump more readily. But I'm very innocent in that because there's probably other factors in there. But I was just making the parallel with my everyday life.
Yeah,
Nico, Roger provides phenomenal images. If you go to the KNC Instagram, I actually just posted your recent one of NGC 2685, which is my favorite of yours, by the way, Roger. So Roger's a phenomenal astrophotographer and makes some absolutely enchanting images.
Thank you.
Raymond says that he has to leave, but thank you for the very interesting subject he hadn't heard of before. Very instructive. Are there any other questions?
Yeah, I guess I have a fast question. This is Mike here. Nico, so does the James Webb Telescope, which is more in the infrared, does that provide additional information, say, on the structure of these clumps compared to the Hubble Space Telescope? Or how about other information obtained, say, from X-rays or radio in different wavelengths?
yeah. There's a reason JWST features, unfortunately, not as highly as the Hubble in these slides. And the reason is that there are science cases for it. They're more niche than a lot of the stuff that people are very, very excited about JWST for. And there's such an immense amount of competition for it that it's hard to make the case to point JWST at these objects. But the reason is that JWST is the infrared cousin of Hubble, as it's often described. It is larger in terms of its collecting area. It's broadly similar in terms of its resolution, which means that we can point and shoot, and it will get a similar image in terms of resolution, but it will get it much faster. So it can cover a larger area in the same amount of time. The problem is infrared is further from the frequency that clumps tend to produce, which is the high energy ultraviolet and bluer visible wavelengths of light. So there is interesting stuff happening in the infrared, but it's not quite. It's not the majority of stuff that clumps are doing that's interesting is happening in the infrared. Most of that actually is in the ultraviolet and the higher energy wavelengths, and that's stuff that Hubble can focus on. The other interesting stuff that clumps are doing are the stuff that is happening at much higher resolution. So if we basically get 10 times the resolution of Hubble at some point, we will be able to point and shoot at the very distant universe and figure out a lot more about these objects. James Webb is not at that point, so it's similar to Hubble in terms of the resolution spatially of these objects. So that's a rambly way of saying JWST has a role to play, but it is not the solution to most of the problems in this field. And that's why just expanding the data set in a lot of different directions, including to higher resolution, to different parts of the universe, that tends to be more interesting in this field. Did that answer your question? And there is a lot more, by the way. There are X-ray. I saw your question on X-ray just now. Shoot.
Yeah, I was just
yeah.
wondering, if they've looked at
Here we
these
go.
clumps, like in X-ray or radio waves, or at different frequencies.
Yeah. One of the proposals oh, go ahead, Christina.
Uh, so yes, JWST does provide additional information on the structure of the clumps compared to the Hubble Space Telescope because it has that near infrared and mid infrared wavelength capabilities. So it's able to see through the dust clouds and able to see more of the structure of individual galaxies, nebula, etc. Go ahead, Nico.
Yeah, I think to piggyback on top of that, the problem that JWST solves in our galaxy and in nearby objects is that it can peer through dust clouds, which is incredible as an ability for stuff where we can see dust clouds in the way. The challenge with clumps right now is to even see the dust clouds. It's just very hard to get the right resolution to be able to even make them out. So there's interesting stuff that's to be probed there. One proposal that was talked about with clumps is that there are certain processes within clumps, and I'm not the expert on this, so I'm afraid to go into detail, and I'd have to Google to get to know more, that generate X-rays or that generate other frequencies. Those would be really interesting to look at because knowing how much those processes are happening, for example, like knowing the number of counts of X-rays that are coming from certain types of clumps versus others, could point to, well, this is probably how those clumps formed and what's happening within them. That, I think, is an ongoing proposal. I don't know if that work is happening, but there are other frequencies that clumps could be examined in that they definitely have not been.
Okay, thanks, Nico.
Yeah, Anthony?
Anthony.
Christina, I should let you handle the questions. I'm sorry. I haven't
No,
been
no,
able to
no,
talk in a
no.
while. Okay, good.
I try to facilitate for all of the guest speakers because I don't know their comfort levels. But Anthony, go ahead in one moment though, because before I forget again, regarding the SDSS and the LSST, the SDSS has something like 0 point has like a typical seeing of like 1.5 arc seconds. And then Rubin
Yes.
has like when you look at the point spread function, like an outer scale like 30 meters, and so it's estimated to be like 0.67 arc seconds. Um, and so like the camera's pixels are designed with a pitch of like 0.2 arc seconds per pixel. So Rubin's design prioritizes like minimizing blurring or like, and so this leads to a much sharper view of what we're looking at compared to the SDSS. Uh, and this coupled with that really good depth and the wider coverage um, enables the LSST to explore the universe in a greater scale. And it was actually the SDSS that the LSST was based off of. The LSST uses the SDSS filters, UGRIZY. And then go ahead, Anthony, and then I'll answer your question, Roger, afterwards.
Okay. Well, I'm coming from the Exoplanet Watch background, and so all of the gravity wave and kilonova capture stuff is still just extremely new to me, and I know basically zero about clumpy galaxies except what you've told me today, and I've learned a little bit, believe it or not. But I'm just wondering, and this is going to show my complete ignorance of both fields, but has there been any gravity waves detected from a clumpy galaxy yet? Or is that something that would even be expected? I don't even know.
I think what you'd need in order to get good science out of gravitational waves that has to do with clumps is a much, much, much larger sample size than we currently have. So that is an interesting branch of science. What we'd want to see is like statistics on how many, for example, binary black hole mergers are happening within clumps and clumpy galaxies versus galaxies that don't have them. We are very, very far from being able to do that kind of science because the statistics are messy by their nature. It's just hard to get a large enough data set that we can get a good signal from well, what's the difference between clumpy galaxies versus non? It's not the main effect that's controlling that. So we're many generations of gravitational wave science away from being able to do that for this kind of problem. I don't think it's impossible. I think it's a really interesting question.
It's a
just
really
that
good question. It has a lot of foresight in it. And the reason why Kilonova capture and the field of multi-messenger astronomy is interesting is because it's a field still in its infancy. Remember, 2015 was the first time Einstein was proven correct for this science matter, and 2017 was when we first detected a optical progenitor for it. And there has been many of that population since. So LISA is going to be a space-based interferometer that's going to present, yes, better data, but also the noise of the amount of gravitational waves coming at it will create another issue, which is there's going to be too much data inundating these sensors. And now it's a really good environment because there's no ground, there's no seismic activity. Humans are the number one cause of seismic activity on the planet, so we get a lot of noise from that, and we know what that sounds like. In space, we're going to be seeing, or we're going to be detecting gravitational waves in such a massive number for LISA that we're not going to be able to distinguish it. And so as this improves, as the algorithm improves, as LISA develops, as LISA gets launched and begins to function, yes, several iterations of this, generations of scientists will improve the catalog that will be able to organize, where are gravitational waves likely to come from, what galaxies, could these clumpy galaxies, with, maybe galaxies with higher producing stars, be producing the ones, are the galaxies that produce gravitational waves in more likelihood. But that's, like Nico said, many generations off.
Okay, thank you. But as far as the speed of the things going, it's kind of scary because I mean they didn't really confirm the first exoplanet with a transit until 1995, and by that time I was already out of school and practicing. So now I'm just recently retired. This stuff is coming down fast and furious, and the amount of data that they're getting from Rubin, it just blows me away. So I could see that there would be a very big need to, I don't know if simplifying some of these procedures for citizen scientists would be accurate or a good way to do it, but there have to be aspects of analyzing individual images that could be whittled down to just a few basic steps that human brains could currently just kind of sort through rapidly without, with
Basically, that's what
would be
machine learning algorithms are. So you break it
right,
down to its Lego pieces. Oh, Roger, I
right.
almost forgot your question.
Okay.
So your question is, will the upcoming extremely large telescope provide better views of these clumps?
So I wish I could answer. I've been out of the grad school game for about a year. So can someone remind me of what the extremely large telescope is?
So we have a 1.5 arc six. Anthony, was that the last part of your question? I'm so sorry.
It was. Thanks. I appreciate it.
No problem. I noticed we were running over time, so I wanted to be respectful of that. So if there are any more questions, please send it now so I can answer them, or Nico and I can answer them. But the extremely large telescope, think about it this way: 1.5 arc second for SDSS, 0.67 for LSST, 0.05. Is it 0.05 or 0.005 for extremely large telescope? So the ALT under ideal conditions has an angular resolution of 0.005 arc seconds. And so the extremely large telescope will be able to resolve much better, many magnitudes better than the LSST. It will have 6 times better resolution than the JWST as well. It'll allow it to take much clearer images of exoplanets, and therefore see anything of a not great resolution or a greater distance with better acuity.
And just to remind me, this is my question now, I guess. The ALT is which wavelength?
Uh,
So I'm
I think it's an
remembering
optical near infrared telescope.
Yeah, I mean, absolutely yes. Higher resolution optical data is the thing that's going to make the field of clumpy galaxies, as well as a lot of galaxy research in general, take off. And I think when that happens, just to keep things on theme, but also because it's very much on my mind, the role of citizen science will explode for galaxies because it will no longer just be, is this galaxy a spiral or an elliptical? What are its sort of global properties? It won't just be where are the interesting sub features of those big features. We will be able to zoom in with higher resolution on all of the sub features within each galaxy, and there is much more interesting stuff and a much greater variety of stuff happening at that scale. So what we'll be looking at is no longer stuff like this, like where is this blue blob in the galaxy and does it exist? We'd be looking at stuff like this, image A over here. What is going on with this Y-shaped pattern? Exactly how many subblobs are in this larger blob? Those sorts of problems, without even expanding the number of galaxies in our sample, are just going to explode the number of problems that we need to answer and the complexity of the answers. So there's going to be a huge change in the way that we do galaxy science once we have a large enough sample of that resolution. I'm very impressed with the questions, by the way. This is I came charging in with a galaxies talk to a group that I know has not seen this before, and I did not simplify these slides very much from what I presented to my PhD committee. So I very much appreciate everyone coming. This is not a goodbye if there are more questions, but I am very grateful to know more about this group and what you all do, and I am happy I could make it.
Yeah, you are, Nico, since you and I are so professionally and personally, involved with each other, you're welcome to join the KNC group chat or Slack. And we have these webinars about once a month, pausing for August unless everybody disagrees and they're like, no, we want to go see one on vacation. We just about once a month, and I have some, pretty interesting members from the community come in. And now that cosmology has, piqued the interest of a few of us, I could bring in a few more members for galaxy studies and stuff like that. But are there any other questions? Nico, is there anything else you want to say?
No, I should sign off somewhat soon. So I think I'll help wrap things up. But just that I'm grateful to be here and that this is a fascinating group that I keep hearing wonderful things about, and I'll be looking for your progress in the future.
All right, thank you so much. And thank you, everybody. Check out Roger's images on Instagram as well. And thank you all for contributing to the interviews. I know I have a few interviews with you guys this week. And for those of you who are filling out the form for the interviews, please do that as well, so I can start getting that together over the August break. Thank you, Anthony. Thank you, Michael. Thank you, Roger, and everybody else who participated and came today. Thank you so much.
Thank
Have a
you.
great day, all.
Yep.